very delighted to participate in this meeting. And I know that my talk is the last one, but I am not going to I'm going to explain just some theoretical ideas, pretty simple ideas, which refer to parametric resonances in ferromagnetic media, and my co-authors is Mike McConey and Mike Page. Okay, in my talk, I briefly explain motivation of this work. So magnetic systems can be considered as adaptive systems. So we apply external microwave or other fields, and we change the state of magnetic material. So it is still magnetic, but it has some excited states, and we can use the states for devices, for magnetic devices. First, I will just show briefly a calculation of parametric resonance of all orders. This technique is pretty simple, and any able student can repeat it. And I have to say that this technique is much easier than usually used in books, in classical mechanical books. Then we'll consider parametric resonance in ferromagnetic grain, and finally excitation of spin waves in bulk samples and thin films. And I will finish with some conclusions. Okay, the basic task of magnetic dynamics is to study the frequencies and relaxations of magnetic excitations, spin waves. This problem is well developed, and every new magnetic material is just studied regarding the spectra and relaxations. But if we need to develop, if we need to go further to develop some devices, we have to know what's going on if we apply not just weak fields, but more or less strong fields, and we change the properties of material, and we can use these magnetic materials together with excitations to develop some useful properties. And the advent of Soule's pioneer work in 1957, when Harry Soule showed that ferromagnetic resonance could be non-linear, and he explained it using parametric resonance, that placed parametric resonance of spin waves in a microwave field as one of the primary methods for studying the dynamic properties of magnetic materials. And parametric resonances are excited exponentially quickly, not like ferromagnetic resonance, which is linearly excite the amplitude, and force the magnetic system to adapt to new states. And the study of these adapted states is of interest for the development of microwave devices. Let's consider the simplest system which exhibit parametric resonance. Everybody knows it from childhood. It's simple example of parametric resonance, pumping the swing by standing and squatting. In this sequence, so the kid is squatting, then standing, and again squatting and standing. And so the kid here works with doubled frequency, and the doubled frequency excite the frequency of this swing. But kid can be lazy and just squatting once, not squatting in the back motion. And in this situation, we have excitation of the swing only with the same frequency. In general, pumping frequencies could be equal to 2 omega divided by n, and n is just, in this case, is n1, in this case, n2. And if kid is more lazy, it would be 3, 4, and so forth. And interest this excitation is that using a lower frequency, we can excite higher frequency in a pretty linear and simple system. So let's consider simple example of harmonic oscillator, say LC circuit with some damping. So if we have, we can consider just like Hamiltonian of the system, which here is the energy accumulated in inductivity, and this energy accumulated in capacitor. And we just modulate the length between these two plates of capacitor. We modulate the frequency. And we see that if we have, okay, if we can transform this Hamiltonian to complex variables. This is very similar procedure like in quantum mechanics. Hamiltonian is transformed to creation and annihilation operators. But in our case, these are just complex variables useful to analyze the system. And the Hamiltonian is just look like a conventional harmonic oscillator Hamiltonian in quantum mechanics, but we have modulation of frequency and we have non-diagonal terms with some modulation. Okay, why it is very complete? Why this procedure is very useful? So usually we deal with a second order differential equation. So, and the analysis of this equation is pretty complicated and cumbersome, and we can consider only several parametric resonances. But in case of complex variables, we have not this second order equation, but the first order equation. And this equation is similar to second order equation, completely similar. And we can just remove time dependence from the equation, introducing another complex variable. C is the so-called slow variable, and we can describe every resonance using this simple equation, just first order equation, and the resonance in this case is just omega equal omega 2 omega naught divided by n, and f is just a Fourier coefficient of this function. And say for harmonic modulation of the frequency, we can immediately write this equation for the threshold field when parametric resonance starts, and approximately this threshold for any n can be described by this simple formula. And there is one more feature, that this with n this threshold not going to infinity. It's finite number. So the higher resonance, the low, the difference between threshold fields decreases, and at infinite n, it's just some number, and it doesn't depend even on damping. Okay, this developed theory is applicable to the parametric resonance of a ferromagnetic grain. So let's consider simple model of ferromagnetic single domain grain. So this grain has uniaxial anisotropy along z-axis. It has some direction of magnetization and external field H naught. And in this system of coordinates, so it's just energy of this single domain grain consists of uniaxial anisotropy and Zeeman energy, and plus we apply external field. In terms of just quadratic deviations, the system can, the energy, the quadratic part of the system, it looks like the energy of harmonic oscillator with some parameters, and we just modulate diagonal part. With harmonic modulation, we can immediately obtain similar equation for any n, for the threshold of any n, and we have approximate formula from this exact formula obtained in resonance approximation, and we see that finite threshold is, we have a finite threshold even at n coming to infinity. So we can use very low frequencies with high amplitudes to excite parametric resonance in the ferromagnetic grain. So parametric resonances of all orders in a ferromagnetic system, more complicated case. So if we have, in previous case, we considered just uniform rotation of magnetization and neglected spin waves in this grain. But now we consider thin film or bulk material and spin waves. So if we apply just a uniform field and perpendicular to the magnetization, we can excite linearly ferromagnetic resonance. But if we apply frequencies above the spectrum of spin waves, then we can excite so-called parametric pairs, waves which move in with half frequency, but these waves move in the opposite direction. And you see that this product of two waves moving in opposite directions give you uniform motion of the media. It's not a standing wave, it's a parametric pair in the media. And this is just a figure with demonstrating. So we apply frequency. This is frequency versus K. We apply frequency at this point, and we excite two spin waves with half frequency and moving in the opposite direction. And in this case, one photon is just transformed to two magnons moving in the opposite direction. And this parametric resonance or parallel pumping is well developed and well known in magnetic dynamic community. But what if we apply several photons here. So original photon frequency is here, but we apply the several photons, and in this situation we have nth parametric resonance, which excite the same pair, and in this situation, n photons spin wave or magnon pair, and we need just overcome the threshold of this process. And we can write similar to previous calculation quadratic energy in terms of spin deviations. So we have modulation of diagonal part. So we have one spin wave moving in one direction, another spin wave moving in the opposite direction, and we have their non-diagonal parts. So if we have just n equal to 1 or main resonance, so the threshold can be easily calculated, and it's well known. If we have all orders, we can obtain this equation. And one more thing, so the threshold of nth of resonance compared to the main resonance is defined by this formula, and actually we can find parameters when this composition of letters is something like 1, 2, 3. So threshold is not that bigger than the threshold of main resonance. So, and the threshold of nth resonance is proportional to 1n degree of damping, and this resonance is just n pumping frequencies, and this frequency is lower, it's below the spectrum, and this n photons excite two spin waves moving in opposite direction, or sometimes it's called parametric pair. This is just an example for quality factor of 100, how this in this dimensionless coordinates thresholds are. This is the main resonance, this is the second resonance, the third, fourth, and so forth, and they become closer and closer to each other. Okay, and how can we prove that we have parametric pair in our system, that we reached parametric resonance? And this could be obtained using so-called modulation method. So we, in addition to steady magnetic field, we modulate it with some slow frequencies, with some we have slow, weak modulation of this field. And if we have parametric pairs in the system, this modulation mixes with parametric excitation. So, and this is just experimental demonstration obtained on the weak ferromagnet iron bore-O3 iron boron. And this is the main parametric excitation on this frequency. This is transmitted through the resonator with the sample frequency. And you see that these two satellites, which correspond to this frequency, modulation frequency, appeared when the threshold is we are above the threshold state. And if we're below, we don't have this two satellites. Okay, so higher order parametric resonances can be achieved on system with low damping, for example, on magnetic systems with nano sizes. And conclusions, we demonstrated the possibility of studying collective magnetic excitations, spin waves, and magnetoelastic waves. It's like spin waves as well, using higher order parametric resonances. The parametric excitation of high frequency collective magnetic oscillations can be achieved by using alternating magnetic fields of the lower frequency. The modulation method in parametric resonance of spin waves is shown to be a powerful tool for studying the adaptation of the magnetic systems to powerful microwave signals. And our research is of interest for magnetic materials of nano sizes. In this case, the relaxation of collective magnetic oscillations significantly decreases and the thresholds for higher order parametric resonances become experimentally achievable. This is just my book, and thank you. Questions, please.